Welcome back to another explainer produced by Forge College. So, in our last session, we took a deep dive into ownership and move semantics, right? And now that we know exactly how to securely handle our digital assets, we're immediately facing an entirely new challenge. Basically, how do we process them in bulk? Look, doing this safely is honestly one of the absolute most critical skills a Web3 developer can ever master. So today, we're going to be talking all about loops and iteration patterns. Let's get right into it.
Okay, so let's start with a simple yet honestly kind of terrifying question. What actually happens when a loop goes infinite? If you're coming over from Web 2, an infinite loop is, mostly just an annoyance. It freezes up your browser tab, you let out a heavy sigh, force quit, and move on with your life. But in Web 3, oh man, an infinite loop is a full-blown financial disaster. It doesn't just crash harmlessly. No, it goes on a massive spending spree, completely draining your smart contract by burning through all its gas until it is totally bankrupt. We're dealing with an incredibly high-stakes environment here where bad code literally costs real money.
To get a handle on this, here's our roadmap for today's explainer. 1. Intro to the repetition problem. 2. Meet for and a while. 3. The blockchain gas constraint. 4. The conveyor belt model. 5. Safe iteration patterns. And 6. Conclusion and next steps. Let's kick things off with Section 1. Meet, for, and while. The absolute basics of Solidity iteration.
So up until now in our smart contract journey, we've mostly used conditional branching to decide if a single operation runs. But when we're dealing with collections of items, we absolutely need loops to decide exactly how many times an operation runs. Otherwise, we're just constantly duplicating our code. If you've coded in C or JavaScript, this syntax is going to look right at home. First up, we've got the structured three-part for loop. This setup gives you your initialization, the condition that's evaluated before each run, and the post-iteration step. All of that makes it perfectly suited for explicit, precise counting. Alternatively, the while loop is kind of your minimalist option. It literally just evaluates a single condition before each iteration, completely stripping away the built-in initialization and post-step. Both definitely get the job done, but you'll use them in different scenarios depending on just how predictable your dataset actually is.
Now, inside these loops, you have two incredibly useful control flow tools. Think of break as your absolute emergency exit. Imagine you're searching this massive list for a specific user ID, and hey, you miraculously find it on the second try. You definitely do not want to pay the gas to check the remaining 1,000 items, right? So you use break to drop out of the loop entirely and save those funds. Continue, on the other hand, well, that's your skip button. Let's say you're processing automated payouts, but you hit an account that's flagged or suspended. Calling continue just skips the rest of that specific iteration and moves straight on to checking the next account. Both of these are just brilliant tools for saving precious computation time and ultimately keeping your contracts efficient.
Moving right along to Section 2, the blockchain gas constraint and why unbounded loops are fatal.
Okay, the crucial point you absolutely must burn into your brain right now is this. Every single iteration consumes gas. On Ethereum, and honestly similar chains too, computation is never, ever free. Every single time your loop cycles, whether it's just reading a tiny value from storage, allocating memory, or doing some incredibly basic math, it adds to a running toll. It is exactly like a taxi meter that just keeps ticking up with every rotation of the tires. And if your loop iterates too many times, the meter climbs way too high and it hits the block gas limit. When that happens, boom, the entire transaction violently fails and reverts, leaving you with absolutely nothing but a lost gas fee. Your state changes all roll back, but the network? Yeah, it keeps your money for the effort. Ouch.
Which brings us to Section 3, the conveyor belt model. This is a great mental model for writing safe loops.
To make this abstract idea of on-chain iteration a bit more tangible, I want you to picture a factory conveyor belt. As a smart contract developer, you essentially have three primary control knobs here. First, the belt length. This is your bound, or exactly how many items are loaded onto the belt at once. Second, the worker effort. This represents the gas spent per iteration. You really need to ask yourself, is the worker just glancing at a box, or are they doing heavy lifting on it? And finally, halting. You need to know exactly when to hit the emergency stop using those break or continue tools we just talked about. Your ultimate goal as a Web3 architect is really just to keep that belt as short as possible and the worker's job as light as possible.
Let's look at Section 4, Safe Iteration Patterns, or in other words, keeping the conveyor belt running smoothly.
Let's actually apply this in practice with some hard do's and don'ts. Okay, First up, do use memory arrays for temporary inputs. Memory is cheap, it's fast, and it is highly safe. Also, do cache the array length in a separate variable before the loop even starts. If you don't do this, your smart contract might end up wasting precious gas rereading the length from memory or storage on every single cycle. And let me tell you, that adds up fast. Okay, now for the don'ts. Don't perform heavy storage reads or unbounded writes inside your loop body. Writing to the blockchain's permanent storage is literally the most expensive thing you can do. Doing it inside a loop, that is pure financial suicide. And whatever you do, don't mutate or change the array's length while you're mid-processing. That is the exact equivalent of trying to add or remove sections of a conveyor belt while it is running at full speed. It just leads to massive logic errors and catastrophic failures.
So how do we enforce these strict boundaries? Well, we use guard conditions. Adding a simple, highly effective line like require nums length less than 200 before your loop even starts is an absolute lifesaver. Without this kind of check, a malicious user, or honestly even just a severely buggy front end, could hand your smart contract a massive list of 10,000 items. That would force your logic into an endless, gas-guzzling marathon that inevitably crashes the entire transaction. The guard condition acts as a bouncer, right? It explicitly stops the conveyor belt from overloading before it even turns on.
Let's anchor on that number for a second, actually, 200. Look, this is just a hypothetical rule of thumb. It's not some hard mathematical limit, but it perfectly reinforces the exact mindset you need to have here. Keeping the belt short is your ultimate bulletproof defense against out-of-gas errors. You really have to remember, the blockchain is a decentralized ledger validated by thousands of nodes globally. It is absolutely not a massive centralized database server like AWS. If you have a dataset that is truly massive, you absolutely shouldn't be processing it all in one go on-chain anyway. The blockchain is for consensus on crucial state changes, for sure, but it is not for crunching big data.
All right, Section 5, Conclusion and Next Steps, Encapsulating Iterative Logic.
Let's cleanly sum up the core principles for safe Solidity loops. Rule number 1, you must explicitly bound your iterations. Like we said, never leave a loop open-ended. Rule number 2, minimize the gas cost per iteration by avoiding heavy storage access at all costs. Rule number 3, prefer using caller-provided memory inputs rather than iterating over heavy storage arrays. And rule number 4, if a dataset is just way too huge, move that processing off-chain entirely or cleverly break it down into smaller, much more manageable batches. In smart contract design, predictability isn't just nice to have, predictability is the absolute ultimate goal.
And I want to leave you with this final, honestly provocative question to ask yourself every single time you write a loop. Can this work be moved off-chain or batched? Keeping this question front of mind will instantly spark better architecture decisions and definitely make you a vastly stronger Web3 developer. Well, a huge thank you to Forge College for producing this explainer. I highly encourage you to head over to forge.college to master more Web3 concepts and get ready for our next lesson, where we'll tackle functions and modifiers to perfectly encapsulate the logic we just learned today. Until next time.